Have you ever thought of making a Breakout style game using the Flame engine but didn't know where to start? Or perhaps you have created the game but struggle with implementing all the physics yourself. If you have nodded along to any of these questions, then you are at the right place. Welcome to channel DevKage. My name is Shubham, and in this video, I'll be addressing those challenges and showing you exactly how to create your own Breakout style game using the Flame engine. So let's dive right in. Before we get into the details of our game, it's essential to understand what exactly a Breakout style game is and how it works. Breakout is a classic arcade game where players control a paddle to bounce a ball and break rows of bricks at the top of the screen. The goal is to break all the bricks using the ball without letting it fall off the bottom of the screen. You'll find multiple variants of this game out there, but at the very core, it all boils down to three key elements: the paddle, the ball, and the bricks. Players use the paddle to bounce the ball upwards, aiming to hit the bricks. Points are earned for breaking bricks, and the game becomes progressively challenging as the player advances through the levels. Okay, now that we understand what we are making, let's kick things off by setting up our development environment. First, we'll need a new Flutter project. So open up a new terminal or command prompt and navigate to the location where you want to store the project. Then create a new project using the flutter create command with the desired project name. I'll name mine as Brick Breaker. Once the project is ready, navigate to the project directory and add the Flame and Flame Forge2d packages as dependency. And yes, we'll be using Forge2d for handling all the physics in this game. But don't worry if you are new to this package. I'll try to explain it as much as possible once we start using it. Also note that I'm using a very specific version of these packages in this video. If you try to use a newer version of these packages, you might run into breaking changes. So be aware of that. Alright, let's prepare all the necessary files in advance. Start by creating a game folder within the lib directory. Then within this folder, create game.dart and world.dart. After that, create an actors folder within the game directory. This is where we'll store all the game entity classes. So inside the actors folder, create a file for paddle, ball, brick, brick zone and walls. Now that we have set up our project and prepared all the necessary files, let's take a moment to understand how Forge2d works. Forge2d is a Dart port of Box2d, a well-known 2D physics engine originally written in C++. This library allows you to simulate realistic physics interactions between objects based on their physical properties. At its core, a Box2D simulation revolves around three main components: the world, which represents the entire physical environment; bodies, which represent the physical objects in the world, such as paddle, ball, and bricks; and constraints or joints, which define relationship and interaction between bodies. A typical usage of Box2D involves creating a world, defining bodies in that world with desired physical properties, and then updating the world every frame to simulate the physics and move the bodies. However, neither Box2D nor Forge2D provide built-in visual rendering capabilities. They focus solely on providing transformation data of the bodies. This is where the Flame Forge2D package comes in handy. It streamlines the integration of physical simulation into Flame-based games by handling tasks such as world creation, physics updates, and synchronization with visual rendering. Cool, now that we have a better understanding of how Forge2D works and its role in our game, let's start by creating the game and the world class. So in game.dart, create a brick breaker game class extending Forge2D game. Similarly, in world.dart, create brick breaker world extending Forge2D world. We can also specify the type of our world class as the generic parameter to Forge2D game while extending it. Then define a constructor for brick breaker game and set the world with the new instance of brick breaker world in the super constructor. With this, our game and world is ready to be rendered in the Flutter widget tree. To do that, go to main.dart and replace the body of the scaffold with a game widget like this. Here, using GameWidget.controlled, make sure that the game factory is invoked only once to generate a new game instance, and the same instance is reused by the game widget on every rebuild. Okay, so with this, now we are ready to run the game for the first time. Watching an empty black window is definitely not the most exciting thing to do, but trust me, the game is actually running and is simulating physics. Here, I'll quickly add a simple circular body to the world and rerun the game. And as you saw, the circular body indeed starts moving downwards automatically. This happens because of the gravitational force acting on the body. Just like the real world, all dynamic bodies in Forge2d world also experience gravity, which pulls them down by default. But unlike real life, we don't actually want gravity in our game. Luckily, it is very easy to control the default gravity for a Forge2d world. We just have to set the gravity in the super constructor of our world class. So to have zero gravity, set it to vector2.0. If I run the game now, you'll notice that the body does not move at all, which is exactly what we want. Next, let's tackle a critical issue that arises when games are resized or played on different screen sizes. As you can see, when the game window is resized, the circular body does not scale accordingly. This means the visible game world is dependent on the window size, leading to inconsistent gameplay experiences. To solve this, we can manually position and scale all game entities based on the window size. But this approach quickly becomes tedious and error prone. Instead, we can utilize a fixed resolution camera to ensure consistent scaling and positioning across different screen sizes. To do that, go to game.dart and in the constructor, set the camera to camera component dot with fixed resolution. The width and height values I've used here might seem too small compared to standard Full HD displays. In fact, such resolutions are normally used for games with pixel art. But in this case, the reason for smaller resolution is how Forge2d works. I'll explain this in a bit. The whole camera system deserves a dedicated video, which I'm going to create very soon. If it is released already, you'll find the link in the description below. For now, just know that the width and height values that we set here, they are used as virtual resolution of our camera. Basically, we can use these fixed dimensions for all our in-game calculations, and the camera will take care of scaling the whole game to match the virtual resolution based on the window size. If I run the game now, we'll get this output. This white rectangle is actually the circular body that I had added. Due to the default zoom of the camera and the small virtual resolution, the body is filling up the entire view of the camera. If you check the documentation for Forge2d game, you'll find that it sets the default zoom of the camera to 10. This is done to avoid reaching the speed and distance limits of underlying physics engine. To understand this further, take a look at the Box2D docs. Specifically, look at the unit section. There, you'll find that Box2D operates on MKS units. That means the unit of length in Box2D is meters. So, if we use the pixel dimensions to create bodies in Box2D world, those bodies will be unrealistically huge. For example, the radius of the dummy body that I have created is set to 20. For the physics engine, this means the body is 20 meters in radius, which is roughly equivalent to a 12-story building. So clearly, we cannot use a 1-to-1 ratio between pixel units and Box2D units. That is the reason why Forge2D game uses a zoomed camera by default. It essentially forces the users to scale down the bodies to make them fit into the game world. But in our case, we are already using a smaller virtual resolution, and technically we don't need the 10x zoom. So override the onload method of brick breaker game and set the camera.viewfinder.zoom to 1. If I run the game now, you can see that the body is completely visible again. Although this works, we are still using a 1-to-1 ratio between the virtual resolutions unit and Box2D's unit. To fix this, introduce a length factor in the brick breaker game class with its value as 0.1. Next, multiply this factor with the virtual width and height. This essentially means our physics world will be 18 by 32 meters in size. Now we just have to keep in mind to use this length factor while setting up the bodies in the world. For example, in world.dart, I'll have to multiply the radius value with the length factor to scale it to correct size. By implementing these adjustments, we ensure that our game entities maintain realistic physical dimensions and consistent scaling across different screen sizes. This completes our initial setup for the game and world class. Before we dive into adding walls to our game, let's take a moment to understand some key concepts in Forge2d: shapes, bodies, and fixtures. Shape, as the name suggests, defines a geometrical object. Forge2d supports various shapes including circles, polygons, and edges, allowing us to create a wide range of objects with different shapes and sizes. Next, bodies are used to represent physical objects in the game world, such as a player character, a ball, or in our case, the wall of the Breakout style game. Bodies have various properties like mass, velocity, and position, and they interact with each other based on physics simulation. Finally, fixtures are objects that bind shapes to the bodies and define their material properties such as density, friction, and restitution. Now that we have a basic understanding of these concepts, let's proceed with adding walls to our game. Unlike many other tutorials that create separate bodies for each wall, we'll create a single body with multiple fixtures to represent all four walls. This approach is more efficient and takes advantage of Forge2d's capabilities. First, we need to create a walls class that will represent our walls. In this class, we'll define a single static body with four fixtures to represent the top, bottom, left, and right walls. The game size parameter will be fixed resolution of the game, and wall thickness will define the thickness of the walls. Our walls class extends body component. Body component is a base class provided by Flame Forge2d that integrates a Forge2d body into a Flame component. This makes it easier to manage and render physical bodies within the Flame engine. In the body definition of the super constructor, we will set the type of the body to static. By setting the type to bodyType.static, we ensure that the walls do not move or respond to forces. Next, let's use the fixture definitions list to define fixtures for each of the four walls. A fixture definition needs a shape as input, and since the walls will be rectangular, we'll use polygon shape and make it into a box by calling the setAsBox method on it. The parameters to setAsBox are half width, half height, center position, and rotation angle of the box. All these values are straightforward to calculate based on the game size and wall thickness that we get as input to this class. Optionally, we can also control the restitution of the fixture in the fixture definition. This controls the bounciness of the fixture. Restitution of 1 means the fixture will not lose any energy when colliding with other bodies, making it perfect for our breakout style game where we want the ball to bounce off the walls. Another important optional parameter is sensor. This defines whether the fixture is a sensor. Sensors don't cause collisions but can detect overlaps. In our case, we want to detect the ball when it goes out of bounds from the bottom edge. So I'll set this isSensor flag to true for the bottom wall fixture. Next, let's add an instance of the walls class to our game world. First, we'll add the hasGameReference mixin to BrickBreaker world with the game type as BrickBreakerGame. Then we'll override the onload method and add a new instance of the walls class. For the game size, we can use the virtual size from game.camera.viewport. And for the wall thickness, you can use any value, but just make sure that you also apply the length factor. And that completes the setup for walls for now. If you run the code right now, you should get an output similar to this. The ball is a dynamic entity that will move and bounce off the walls and pedal. We'll create a ball class for this, and similar to the walls, we'll extend the body component. The constructor of the ball takes two optional parameters, radius and position. These parameters allow us to define size and the initial position of the ball. In the super constructor, we'll define the body definition for the ball. We set the type of the ball to dynamic, which means the ball will be affected by forces like gravity and collisions, making it move and react to the environment. The position parameter sets the initial position of the ball in the game world. We also set fixed rotation to true, which ensures that ball does not rotate. This is because for a circular ball, rotation does not affect the gameplay. So we fix it to simplify the physics calculations. Additionally, we set the bullet parameter to true. This flag ensures continuous collision detection, which is important for fast moving objects to prevent them from tunneling through other objects. Next, let's define the fixture for the ball. We create a circular shape for the ball with the given radius using a circle shape. This defines the physical shape of the ball. We'll also set the restitution to 1, making the ball perfectly bouncy. This means the ball will retain its speed after colliding with other objects, which is crucial for the dynamic and fast-paced nature of a breakout game. Now, to make the ball move, we'll need to apply some initial force or impulse to it. To do this, we override the onload method in this class and we apply a random linear impulse to the ball. This will make the ball start moving as soon as the game begins. Next, we want the ball to maintain a constant speed. This can be done by overriding the update method. We do this by calculating the difference between the target speed and the current speed of the ball. If there is a difference, we apply an impulse in the direction of the ball's movement to correct the speed. This keeps the gameplay consistent and ensures that the ball moves at a predictable speed. The reason we include the ball's mass in the impulse calculation is to ensure that the force applied is proportional to the ball's mass. In physics, the impulse needed to change an object's velocity is directly related to its mass. Impulse is mass times change in velocity. This ensures realistic and consistent behavior regardless of ball's mass. Now, to add the ball to the game, we'll go to our Brick Breaker world class and add an instance of ball in the onload method. I'll set its radius to 4 and initial position to be the center of the screen. And just for testing, let's go to the walls class and remove the isSensor flag from the bottom wall fixture. This will ensure that the ball remains within the game window. If you run the game now, you should see an output similar to this. Okay, now let's add the paddle to our game. The paddle will be a kinematic body, allowing it to move left and right in response to the player input without being affected by other bodies and forces. First, we need to create a paddle class that extends body component in the paddle.dart file. In the constructor, we take the size of the paddle and an optional position as input parameters. In the super constructor, we set the position of body definition to input position. Next, we set the type to bodyType.kinematic. Kinematic bodies are controlled by user and do not respond to forces or collision with other bodies. We also set allow sleep to false to prevent the paddle from sleeping. For the fixture definition, we use a polygon shape to define the rectangular paddle and set its size with set as body xy. The parameters to set as body xy are half width and half height. Similar to the previous fixtures, we set the restitution to 1 here as well. To handle the keyboard inputs, we add the keyboard handler mixin to paddle class and the has keyboard handler components to the brick breaker game class. Next, we add a double member in the paddle class called h-axis. This will store the horizontal movement input for the paddle. Next, we override the onKey event method to handle key inputs. The value of h-axis will always be set to 0 at the start. Then based on the left and right inputs, we will subtract or add 1 to h-axis. To move the paddle horizontally, we override the update method and change the linear velocity of the body. We do this by setting the x component to h-axis times max speed. But since the paddle is a kinematic body, it won't automatically stop when it hits the walls. We need to manually detect this and set the velocity of the paddle to 0. For this, we introduce a private getter called isAtLimits, which returns true when the paddle is very close to the edges and the h-axis input is in the direction of the corresponding edge. Then in the update method, if isAtLimits is true, we set the x component of the velocity to 0. To test this, let's go to the Brick Breaker world and add an instance of paddle near the bottom center of the game. If you run this, you should be able to control the paddle and the ball should bounce off the paddle. Although this seems to be working fine, there is one problem. If you have played any good breakout game before, you must have noticed that the ball's bounce direction can be controlled based on the paddle's movement. To demonstrate this, set the initial impulse of the ball to be vertical. On running this, you'll notice that the ball does not change the bounce direction even if the paddle is moving when they collide. This happens because there is no friction between these bodies. We can easily change that by setting the friction to a non-zero value in the fixture definition of both these components. Now, if you test this, you'll notice that the ball's direction can be affected by the paddle's movement. One more thing, if you want the ends of the paddle to be rounded, you can do so by adding two more fixtures to the paddle. These should be placed at the ends of the paddle and should use a circle shape with the radius equal to the height of the paddle. Here is a glimpse of how it would look with rounded ends. This completes the setup for our paddle. Now you have a paddle that moves left and right based on player input and can interact with the ball in a more realistic way. In this section, we'll add the bricks to our game. To do this, we'll create two classes, Brick and Brick Zone. The Brick class represents individual bricks, while the Brick Zone class helps us define a rectangular region where the bricks will be placed. So let's dive into the implementation. First, let's create the Brick class. This class represents a single brick in our game. We'll define it in the brick.dart file. The brick class extends body component, and in the constructor, we set the position and size of the brick as required parameters. In the super constructor, we set the body definition with the type as bodyType.static and position as the input position. By setting the type to static, we ensure that the bricks do not move or respond to forces. This is crucial because we want the bricks to stay in place when hit by the ball. The fixture definition uses a polygon shape with the setAsBoxXY method to set the brick size. We pass the half width and half height to setAsBoxXY. We also set the restitution to 1 to ensure the bricks are bouncy when the ball hits them. Next, let's create the Brick Zone class. This class will help us define rectangular region and populate it with bricks. We'll define it in the brickzone.dart file. The Brick Zone class extends position component and not body component. This is because Brick Zone itself does not need to interact with the physics engine directly. Instead, it serves as a container for the bricks and helps in positioning them. In the constructor, we take the position, size, number of bricks in x and y direction, and the spacing between the bricks as parameters. We calculate the brick size based on the total size of the zone, the number of bricks, and the spacing between them. Next, to add the bricks, we override the onMount method and iterate over the number of bricks in y and x directions. For each brick, we calculate its position based on its size and spacing. And then we add that brick to the brick breaker world. Note that body components are always supposed to be added as direct child of the Forge2d world component. And the parent of brick zone is going to be brick breaker world, which is a Forge2d world. But the parent property of any component is valid only once the component has been mounted, which is why we are doing this in the onMount method instead of the onLoad method. Now let's add the brick zone to our game world. We'll do this in the brick breaker world class. So add a new instance of brick zone to the brick breaker world and set the position, size, number of bricks and spacing as needed. Now when you run the game, you should see the bricks arranged neatly in the defined zone. By using the brick and brick zone classes, we can efficiently add bricks to our game. The brick zone class helps us define a region and automatically populate it with bricks, making it easier to manage and customize the brick layout in our game. Now that we have got all the core entities of our game working, let's see how to handle collision between these entities. First, we need to set the user data of the body definition to this in the constructor of ball, brick, and wall class. It is necessary for the user data of bodies to point to their corresponding body component if they want to get notified of collisions with other entities. Next, we add the contact callbacks mixin to the ball class. This will allow us to override the begin contact method. In this method, we can check the type of the other colliding component and perform game-specific logic. For example, if other is of type brick, we remove that brick from the game. If you run this, you should see an output similar to this. The bricks should get destroyed when the balls hit them. Next, we can make the whole game reset when the ball collides with the bottom wall. To do this, first we'll refactor the code from the onload method of BrickBreaker world into a new private method called start. Then we add a new public method called reset, which removes all the children of the world, wait for some time, and then calls the start method. In the ball class, we add the parent is a mixin with the type as BrickBreaker world. This mixin exposes a parent getter which returns the parent component with the given type if it is valid. Then in begin contact, we check if the other component is of type walls and if any of the two colliding fixtures is sensor. If so, we simply call parent.reset method. If you run the game now, you'll notice that the game resets every time the player misses the ball. And there you have it. We have successfully built a basic breakout style game using Flame and Forge2d. We started by setting up the walls, then added the ball, paddle and bricks. We also implemented collision handling to make the game interactive and challenging. While we didn't cover score calculation and UI elements in this video, you can refer to my other tutorials where I've explained those concepts in detail. Adding a score system and UI elements would be a great way to expand on this project and make it even more engaging. Remember, game development is all about experimentation and iteration. So feel free to tweak the game mechanics, add new features, and customize the visuals to make the game your own. If you found this video helpful, please give it a thumbs up and subscribe to the channel for more game development content. If you have any questions or suggestions, leave them in the comments below. I hope to see you in the next video. So until then, happy coding and bye bye.